People, engineers like you and me are also building companies because they see value that they can deliver to different customers, global government, and also private industries if they measure atmosphere measurements, right? So here again, you were able to see one more GHG sat, one methane sat, and all of these are from private companies, right? So, and this is the satellite kind of way. But there is another section where you're not viewing Earth from satellite, but you're viewing Earth from ground, right? So these are the kind of sensors that are there that actually track the sun, because we know what is incoming radiation from sun. If it different from what we expect, we can say what is the kind of aerosol that is there, what is the kind of gases that are there. And this is also a growing industry, Earth based sensing of space. So at that point, we can know what is the kind of methane that is there. So these are all a part of weather stations that we talk about. So as I told you, there's a satellite-based measurement also, and we will just see an example, right? So this is a example of a MODIS satellite here. This is from Google Earth Engine. So what Google does is it catalogs a lot of different satellites, and we have a live, almost live picture whenever the satellite measures. We have a live picture of what satellite is taking, right? So here you can see that optical depth is larger in South India than in North India, because probably we might have a lot of industries, right? And there's other kind of things that affect this as well, the flow, the jet streams, and the wind velocities in different layers of the atmosphere. But then the information is available by public satellites at a larger resolution. Like this is an example of MODIS, right? So if you are interested in studying how the, and I'm just plotting optical depth here, and there are multiple parameters here as well. So it is on you to research and see what is the global trends, what we are not able to do, how we can innovatively do that, apply AI and try to measure different parameters that are important for global ecosystems, like that, right? So this is an example that I'm showing. Even India also has such platforms, which we will talk about. And one more thing is spectrometer. Now we have only seen that the satellites are observing Earth, right? But there are also some kinds of satellites which emit their own radiation, not just look at reflected sunlight, but they emit their own radiation in microwave, and then they observe the reflected radiation which they emitted. So based on the reflected radiation, they can know what is the texture like, right? So when they know what is the texture like, if it's a rough surface, there's going to be a lot of noise, right, in the oceans. So based on the noise patterns, they can say how much is the wind velocity there, and the other parameters also, right? So these are different kinds of satellites, right? So this is an optical based satellite in different bands. It is observing Earth. This is a kind of satellite which is sending radiation and measuring the reflected radiation and trying to predict wind velocities, right? And there are different kinds of satellites like sounders. What they do is they look at the edge of the Earth, and they see at different heights what is the kind of material that is there, right? So for example, here you can see the electron density with respect to height, and then there is temperature, pressure, and all that, right? So when they see at the edge of the Earth, they can see all the atmosphere height that is there. So these are called sounders, right? So this is the basic understanding of atmosphere we have, and there are other kinds of satellites as well. But basic understanding is we can solve a lot of problems and also estimate what is the behavior of atmosphere from such kind of satellites. Next thing we will be coming to is planetary studies. So here we have seen in the atmosphere satellites that okay, we measure certain kind of elements and also certain kind of parameters. Now when we want to understand planetary things, there are again subsections here. There are planets, there are moons of planets, there are asteroids, and there are comets, right? So what is the use of studying planets is we understand how the planets were formed, what is the geology of different planets. Maybe it can info something about Earth itself. And there is chemistry of the cosmos, how the universe was formed, how different planets were formed, how even the moons of planets were formed. And then there is atmospheres, right, for different kinds of planets, right? So Earth is a terrestrial planet. Jupiter is mostly a gas, right? So the thing is, on Earth, you can imagine if you land from the atmosphere on Earth, there is a crust, right? So you are able to see terrestrial feel is there. On Moon also, it's a solid surface. But on Jupiter, Jupiter is so large that it has stayed like a gas giant, right? So it's almost a gas, right? Jupiter is almost a gas. The core component of Jupiter is not well yet understood, but it is understood that it's a small part. Most of it is a gas. And the planets starting from Jupiter, Saturn, Uranus, Neptune, most of them are gas giants, right? So atmosphere has a large role to play in it. Even if you see images of Jupiter and Saturn, it's almost like there are very, very big storms, almost the size 10 times of Earth, the storm is going on. So you can imagine the kind of atmospheric science that we can study from Jupiter and how we can infer it on Earth and also in the planetary sciences. Then we can do a lot of physics, oceanography, hydrology, and on Mars you were able to see from Mangalyaan images. If you have seen, there are a lot of channels, right? It is estimated that some kind of fluid flowed on Mars years ago. So kind of hydrology that was there, and theoretical planet science and glaciology based on the polar ice caps that are there on different planets, right? So I'm just taking an example of Chandrayaan 2. So Chandrayaan 2 was a satellite, an orbiter. There was a rover also, but we all know what happened. So Chandrayaan 2's orbiter had these kinds of payloads, right? So whenever you see even NASA's rovers also, or even orbiters also, you will see there are different kinds of payloads. See, from this talk, what I want you to understand is confidently go to different websites of planetary orbiters and try to understand what these payloads are. Okay. First thing is we have terrain mapping camera. So it is a camera that can map different structures on terrain. So it is basically has to look in visible wavelengths. Then we have Chandrayaan 2 large area soft X-ray spectrometer. So it is a spectrometer that we talked about, which operates in X-ray, and it has a large area of coverage. That's it, right? So it this is the instrument summary. So now you understand what this instrument does. Then we have solar X-ray monitor. So what this does is it observes X-rays that are coming from sun, from orbiting moon, right? So this is one kind of payload. The other is orbiter high resolution camera. So we are having here terrain mapping camera. Then there is much more high resolution camera that we have Chandrayaan 2, and we all know that Chandrayaan 2 is the highest remote sensing or highest resolution camera around moon. Even NASA does not have the resolution we have, right? So this is one more high resolution camera operates in visible wavelengths. Then we have imaging IR spectrometer, which is a basic spectrometer which is operating in infrared region. Then we have synthetic aperture radar, which operates in microwave. Basically, what is a radar? Radio detection and reading, right? So as I said in scatterometer, this radar sends radio waves, absorb the reflected radio waves, and forms a science experiment, right? So this is a synthetic aperture radar. We can see radar images on moon also, and most of the data is actually free on ISRO's website called ISSDC, ISRO Space Science Data Center. So you can search it on Google and you can see almost all data you can actually see on your own systems, how moon looks in different wavelengths. And we have compositional explorer. Again, this we know that it is trying to estimate the composition of the atmosphere. And we all know moon has a very thin atmosphere. So there are some molecules that are revolving around moon also, like we have Earth's atmosphere, but it's not very thick. So we want to measure that. And then there is radio science experiment, right? So just to give a gist of how different payloads look on orbiters, right? And again on Mars orbiter mission, and you can read my paper on Mars orbiter mission. So this is basically having, this is quoting my paper, which is having different payloads on Mangalyaan. We have Lyman alpha photometer, and Lyman alpha we almost have studied in 10th class or even in intermediate chemistry. Lyman alpha is the spin change transition in hydrogen's electron transfer, right? So for example, if a hydrogen atom is actually transferring the electron in hydrogen orbit, transferring from one spin to another spin, a radiation is emitted, and that's how we get Lyman alpha lines, right? So that is the observations that we can do by which we can understand how much is the hydrogen that is there. Then there is methane sensor for Mars. How we do measurement of methane is again, as I told, different kinds of compositional estimations. Then we have exospheric neutral component analyzer. Again, this is also analyzing compositions. Then we have thermal imaging spectrometer. This is a spectrometer in thermal infrared wavelengths that we've seen in electromagnetic spectrum. Then we have Mars color camera, which is again similar to a orbiter high resolution camera on Chandrayaan 2, which is looking at Mars. We have even made an atlas of it available on ISRO's website, right? So I'm just taking you through that. All we are trying to do is trying to get the compositions of planets, trying to get composition of moons, the materials that are there, and this is the science that we are trying to do, right? Now let's move to rover, right? And on rovers, this is a image from NASA's website on a Mars rover. What it has is subsurface radar, that is it emits radar into ground, and radio waves actually penetrate some amount into ground and they get reflected, by which we can understand what is the component underneath the Mars atmosphere. And then we have MOXIE, which produces oxygen from Martian carbon dioxide, which is an experiment. Then we have X-ray spectrometer, as we have studied. So it observes X-ray wavelengths from its instrument. Then we have ultraviolet spectrometer. See, almost all of them are some kind of spectrometers or compositional analyzers. as I have told you. And if you delve deep into how this X-ray spectrometer works, even on Chandrayaan 3 also we have some kind of spectrometer. So if you see, you will realize ki, okay, from the basic science that we studied in engineering or even 12th, what is the kind of advancement that we have had? This is basically engineering stuff. See, the basic science that we need to do spectrometry is already laid down even in the chemistry labs of 12th or even the BTech first year, right? So you do Bragg scattering, right? And then you do kind of spectroscopy itself, which you may not realize that it is a kind of spectroscopy that is used on planets, but it's the fundamental science is same. Only you add some kind of engineering to it so that it is able to tackle planetary environments, right? So basic engineering, you can go to this website and see, you will understand almost lot of things, right? And then there is weather station, there is laser imager, and then there is zoomable panoramic cameras. So these panoramic cameras are even available in our phone. The basic science is same. All is that these cameras are able to withstand the temperature, and the kind of engineering that is built into it is similar to what even our phones have these days, right? So I hope we have realized that okay, planetary rovers, moon rovers are built with some kind of science that we want to do from composition as an understanding. But how do we send this to that particular planet is another kind of engineering, right? So this is Voyager, right? Voyager is a NASA spacecraft which has almost imaged all kind of planets, even Pluto. There is Voyager 1 and Voyager 2. What it used was gravity of different planets to float around in space, right? So as you can see, there's Voyager 1 and Voyager 2 paths here. So Voyager 1, Voyager 2, or in the blue, you can see it has imaged Neptune, Uranus. Voyager 1 has imaged Saturn, Jupiter. And there are incredible images from Voyager's website or even on NASA's website that you can see how closely they have imaged Jupiter, right? So another kind of engineering over and above building satellites and payloads is making gravity, right? Understanding gravity, building mechanical engineering systems that automatically maneuver through this kind of environments, etc. So there is intermixing of different kinds of engineering everywhere. So there's mechanical engineering in building satellites, payloads, rovers. There's electronics engineering, and even here also the kind of communications that we do. Almost all EC students might be knowing communication engineering. There is antennas, and you build antenna equation, right, in EC. So there is QPSK modulation, quadrature aperture modulation. Almost everything is used here, right? So if you study your basics and you at least know the fundamental science at that, all that you need is to apply it in a professional engineering way, and you can build solutions that can do science at this scale. And then there is meteoroids, meteors, asteroids, and comets. These are orbits. These are materials, or let's say objects that are going around sun and are sometimes even coming into Earth's atmosphere also, right? So meteoroids are what? Meteor fragments that reach the ground, right? So there's different kind of definitions, right? All the meteors that you can see are basically objects that are floating around with sun's gravity or planet's gravity. When they reach Earth's surface and they burn in the atmosphere, some part, these are called as meteorites, right? And then there is rocky or metallic fragment of an asteroid, comet, or planet. They are called as meteoroids, right? So meteors and meteoroids, and then there is comet and asteroids also, right? So even you can see it's a very brilliant thing that there are classification of different bodies, right? And there has been, in fact, human landing, right, or crashing or observing these kinds of different bodies also. One example is Rosetta. So Rosetta was a mission by European Space Agency. See, building stuff for reaching Moon or Mars is complicated, but building stuff to reach an asteroid, right, and then communicating with it and delivering science out of it is really difficult, right? So we have to do a lot of engineering on how we will use different gravities and how we will maneuver our inclination and velocities to reach that particular asteroid, right? So we had a asteroid Lutetia flyby by this Rosetta, and then it has imaged the asteroid very clearly to understand also, okay, what is the composition of the asteroid. And then we had stains also, and then finally the mission was to land on a comet. What is a comet? You see, right? Most Telugu students might know, we say it as Toka Chukka. It receives a lot of, it delivers a lot of ice when it goes to sun, and when it goes far away from sun, it builds a lot of ice, right? So it is a comet. So Rosetta has even landed on a comet. So this is an image of Philae comet taken from Rosetta. So in the background, you are able to see ice that is melting from solar heat, right? So These are again instruments on Rosetta. If you go to the website and see, it is having X-ray spectrometer, it is having infrared and visible analyzer, we are having radio wave transmission experiments, right? We are having composition experiments, right? And then we are having magnetometer and plasma monitor, which is basically trying to measure the magnetism of the self-induced magnetism of that comet. And we have a plasma monitor because solar radiation is melting a lot of things. There's some kind of plasma that is there. And then we are also having a sampling, drilling, and distribution subsystem inside that particular mission, right? So this is the kind of reading that you may have to do, because see, you know all the fundamental science. All the thing is you have to understand what is the engineering that is done, and there are different papers on these instruments also. So all that you need to do is open and read, right? So now we have basic understanding of different planetary science and atmosphere. Now we will dwell a little bit deep into how satellites are built, because see, satellite is a something that is bound by gravity to a larger object, right? So we build satellites to be bound by sun, to be bound by earth, to be bound by different planets, like Mangalyaan is a satellite around Mars, right? So almost all these payloads that we are mentioning are a child to a particular satellite that is bound by the parent, right? So there are different kinds of orbits here as well. Now, these are orbits that are valid for any particular body, but imagine that you have an Earth, right? And now we have a low Earth orbit, which is almost till 800 kilometers, right? And then we have medium Earth orbits, which are at 10,000 kilometers, and we have high Earth orbits like geostationary satellites. We have at 35,000 kilometers odd, right? So, what is the different kinds of science that we can do? See, if you are having a low Earth orbit, you can actually see Earth from a crystal clear point of view. Like, for example, Google Maps, they are taken from multiple satellites, but the highest resolution is around 20 to 30 centimeters. That satellite goes at 300 kilometers to Earth, right? So, very close. And then when you go to medium Earth orbit, you can see a lot of Earth, right? So you can do data relay transmissions. And in the geostationary orbit, you have satellites like weather satellites. You are able to see, like in news, they show that new clouds are moving, etc. All of that, what it's able to do, it's able to see India on a whole and even bigger continents also. So how it is done is basically satellite is at a very large distance from low Earth orbits. We call it as geostationary satellites, right? So in this orbit, we have atmosphere satellites and we have communication satellites also. So how communication is done is basically if you are at a very high altitude, you can see almost all Earth. So you can receive signals and send signals to almost whatever is visible to you, right? And that's how communication satellites work, and they are at different orbits, right? So even by understanding orbits and doing orbital mechanics, you can derive a lot of different science, right? So as I said, these are some examples of communication satellites. We have GSAT, Inmarsat, we have Viasat, etc. Then we have observation satellites, which are looking at Earth from very low Earth orbits, like what you see in Google Maps. We have Landsat, Risosat, Resat. This Risosat and Resat are from ISRO. And then we have navigation and data relay. So these are a mixture of satellites which provide signals to Earth to understand where we are. We have GPS, AIS, IDRSS, and there are different satellites as well, which are having different objectives, right? So one basic segmentation is that, as I said, in the spectrometers we have seen there's visible, there's microwave and radio. Even in satellites also, in payloads, we have something that is visible, right? Through our naked eye, that's what the payload is there. And in SAR, we are sending the radiation and getting reflection. So in visible, what happens? Sun has to be there to send the light, and we observe the reflected light in optical or visible. But in radar, what happens is we send our own radiation and observe the reflected radiation. So we see our texture, right? So this is what an example of optical. So this is having red, green, and blue. That's how we are able to see natural color. And this is a texture map that has been taken through radar, right? So one thing that you can see from here is the water is all black. Why it is black? Because satellite is sending radiation and water is like acting like a mirror and it is sending away. It is sending the radiation away, right? So nothing is observed. But for buildings, so imagine there's a building, satellite is sending radiation. The texture is such that it will send it back to satellite. So wherever there is kind of sharp edges or texture difference, we see some radiation there. So this is how we are able to see higher resolution images also. So these are different kinds of payloads only. Okay. And from optical, what you can actually identify, see, as I told, there is spectrometer, right? So optical imaging is also again understanding the behavior of elements on Earth in different wavelengths. Okay. So in optical, there is red, green, blue, near infrared, etc. Right. So if you observe these wavelengths in different spectrums, right, you can actually build some kind of empirical formulas whereby you can understand what is the performance of that material. Okay. This is a vegetation index, which is a simple subtraction and addition of near infrared and red value. Okay, so the formula is NIR minus R by NIR plus R, which is near infrared minus the red value by near infrared plus the red value. So you take a satellite image, do the calculation, and if you see that vegetation index is high, that means plant health is high. If it is low, then the plant health is low or it has just started sprouting, right? So there are kind of empirical formulas that you can build to build economic indicators, right? So these are sellable to anyone. So if you build some indicator which is giving, let's say, crop health, whom you can sell this to? You can sell this to crop insurance banks. You can sell this to loaners like banks, like SBI, whoever is giving loans to farms, so that they are risk free. And even you can sell this to farmers also to predict what farm can grow, and you can also predict what is the kind of diseases that we are having, right? So these are the kind of science that we can do. Okay, and finally we come to space observation, right? So we have telescopes. Okay, so in telescopes what happens is, now we are there are see what happens is, if you are having a telescope, and most of us can buy a telescope at 10,000 to 15,000 these days, and you can observe planets, right? But what happens is, when you try to observe stars, atmosphere is acting like a lens, and atmosphere has winds moving and all, right? So what happens is, when the starlight is coming, it is diverging a lot, and that's why you see twinkling also, right? So telescopy is not actually done best when you do it from Earth. You have to somehow escape the atmosphere and do, right? So if you want to put a telescope in atmosphere, the best kind of thing is that you build a satellite and put a telescope on it and get the data from them through our ground stations, right? So that is the kind of engineering that is done. So for example, this is a Subaru ground telescope, and then we have a Hubble Space Telescope image of the same object. See how blurry this particular image is from ground-based telescopes, and how clear the second image is, right? So this is observed from space, this is observed from ground, that's it, right? And then we have higher engineering missions like JWST recently launched. So this is a, so here what you're seeing is the visible spectrum. Like you are also again observing space in whatever light that your eyes can see. Now JWST, it is launched to observe um, space in thermal region, thermal infrared, right? That our eyes cannot see. So the kind of engineering that it takes to put these into orbits, right? It is also marvelous, right? So just see this example, that see JWST is actually looking at space, but the other side of JWST will be looking at sun, right? So there's a lot of solar radiation that hits JWST, which is called hot side, and then we have cold side. This is where it looks at space. So we have to manage all this temperature difference. We have to manage all the heating that is done on one side to another side, and all that goes into engineering, right? So all the budding engineers in material science, chemistry, mechanical, all of them can build such engineering system, right? So if you put that, let's say now we have all seen Aditya L1, right? So Aditya L1 is placed in the middle and it's observing sun. L2 is exactly opposite. It is placed outside of Earth at L2, and it's facing away from sun. One side is facing towards, which does not observe. The other side is facing away from sun. Okay, and see the kind of difference in the orbit. See, Hubble Space Telescope is rotating at 570 kilometers, around 570. So this is like a normal low Earth orbiting satellite. Now Webb, because it has to stay away from solar radiation, it goes at around 1.5 million kilometers at L2, and it has a halo orbit around L2, right? So different kinds of engineering, different kinds of science, and different kinds of mechanisms that we can build. So as I was telling, if you see Jupiter, you can see large parts of atmosphere, right? So most of this, whatever you are able to see, is captured by James Webb Space Telescope in thermal infrared. That means wherever you are seeing dark, it is cooler. Wherever you are seeing hot, it is warmer, very high temperature, right? So you can even see the rings around Jupiter in observation, like in visual wavelengths. It's very hard to see, but in thermal, it is very clear, and you're even able to see the storm also. So the storm, as I said, Jupiter is a gas giant. Most of it is only gases. It's only a gas body, most of it, right? So here you are able to see how gases interact, different eddy currents that are there in Jupiter, wind flows. See, each of the latitude of Jupiter is having a different kind of temperature and wind flows. Even on Earth, it is the same case. At particular tropics, and when you take to Arctic circles, there are different kinds of wind flows that are there, right? And then again, we come to navigation satellites. And the other kind of interesting stuff is that how do we know where we are in space, right? So on Earth, how do you tell directions? Is basically, okay, come to this KFC, turn left, come to this McDonald's, then you the second appointment is mine. In space, it's not like that. In space, how do you do it? We have a star map established, and we have the database of where the stars are located. So by looking at the patterns of stars, we try to estimate where we are in space. That's how navigation is done. And there are universe objects like pulsars and quasars that are there. Like pulsar is a star that is almost dying. Almost all the gravity has eaten its material, and there is incredible amount of radiation that is coming from poles, right? So if you observe this from Earth, what happens is at particular intervals you are able to see lot of light. Like for example, when it is facing us, you see light. Again some darkness, again light, and these are very periodic. We know exactly what is the period from the physics of a pulsar. So from this, these act as lighthouse inside space. So if we know some kind of pulsars, we can range the pulsar light and we know where we are. So this is also an electronic system and image processing problem, right? So what you do, you build a CCD to observe this kind of pulsars, measure the time length, and you see multiple pulsars like that, and then you just build an algorithm that okay, I'm at this particular point from the database of stars, right? That's it. Simple problem. All you need to do is work on it, get the database, know how the physics is, and build a range. And then even GPS satellites are having different kinds of objects like this, not just pulsars, there's quasars also, and we have a database of these quasars, and we know where these quasars are, and they are almost inertial, right? So from these high energy emitting stars and planets, we can know where we are. There are even sun sensors also to know where the sun is, and now I can know which is the kind of rotation I have, right? And then finally we come to, so all of this is used in satellites, and inside satellites we have spectrometers and all, right? Now we are coming to another part of the problem. Now we are also trying to detect exoplanets, right? Planets of different stars. How do we do that? Okay, the basic thing is, around any star there's a region called as Goldilocks zone, right? If you're too close to star, water evaporates, and if you're too away from star, water freezes, right? So there's a zone where life can exist, or at least life in a our Earth kind of way can exist, right? We are all carbon-based life, carbon, oxygen elements. Almost all of our hand is carbon, right? So how our life can exist? If we want to estimate similar kind of life elements, we look at Goldilocks zone around all stars, so that we have this concept that okay, water may exist there in liquid form, and then life can form, right? But over and above this, we also have a lot of mechanisms to detect planets around stars, right? So one thing is called transit time photometry. So what happens is you continuously keep looking at a star, and when a planet goes across it, we cannot anyways resolve the stars that okay, we can see it like a sun. It's always a point, right? Because it's too far. So what happens is the light that is coming from the star actually decreases because an opaque object is coming before it. So this is the brightness that we have, and because the planet is not in our line of sight, it is high, only we are able to see the star. When it comes into the middle of the star, the brightness decreases. And this is periodic because it's an orbit. Planet is around an orbit, right? So this is called transit photometry. This is how people are able to detect planets that you see in news, that okay, Earth-sized planet has been found in a particular constellation or a galaxy or a star. This is how you're able to see. And there are other kinds of methods as well, like radial velocity. So see how we measure cars velocities using velocity guns is by Doppler, right? So for here also, stars also have a kind of movement, right? So planets and stars revolve around the center of mass. So if a star is moving, right, then what we have is a Doppler shift in the particular wavelength. So when it is going away, it red shifts. When it's coming towards, it is blue shift, like that. So based on the kind of wavelength shift of the star also we can predict, right? And then there is micro lensing, which uses relativity to see the brightness of the star from other stars behind it. And then there is astrometry, which you track the position of the star. So if the star is not actually flowing very smoothly, but it is actually revolving, that means there's something else that is concerning it, right? And then there is direct imaging of planets, which is not really possible because we cannot resolve so much, right? So these are the kind of science that is happening. And see, when I told you all this, right, instrument building is anyways where we build a camera or even a telescope also, you can imagine this. See, all you need to do is the data is open source, right? All the kinds of satellite observation telescope is open source on NASA, ISRO, everywhere. All you need to do is build an algorithm software to measure these kinds of shifts and publish it. That's all there is, right? And that's how people are able to detect planets. PhD students and tech BTech students also detect a lot of such phenomenon happening, right? So I hope I have shared with you almost all kinds of things that we do in space, from observing Earth atmosphere to satellites and planets. And I'm open to any questions if you have, and I might have obviously missed a lot of things, but I hope, I'm sure I have motivated you enough to look into this from your engineering background. Thank you. That's it. Can organizers take over? Yeah, and also if you have some questions, I'm always open to interact with you. This is my LinkedIn URL. So yeah, if you have any questions or some guidance you need or some doubts, you can always speak to me. Yep.
Hello,
Yeah, please.
Sindhu. Please continue. So thank you, sir Radhakrishna sir, for accepting our invitation,
Yes,
taking
sir.
the session. Please continue, sir. Is
Okay, sir. On the behalf of Department of ECE and Convenience and students, I extend a very heart vote of thanks to the Honorable guest Radha Krishna sir, who blessed us his valuable time despite of his busy schedules. The session was very informative and inspiring as well. Thank you for accepting our invitation, sir. And
Yeah.
we expect this kind of sessions in future also. And
Yeah.
now I would like to extend a special thanks to our HOD sir and conveners of the program for providing support and great encouragement. Thank you all for your interest and contribution.
so, any queries from the audience side? You can also drop a text message. Thank you, sir Radhakrishna sir. Thank you for accepting our invitation. Like in near future, we'll see more events from your side.
Most welcome. Most welcome.
Thank you, sir. Really, thank you. Okay, sir. I'll give you a call, sir.
Okay, fine. Thank you. Thank you everyone for patiently listening. Bye.